Hello everyone, welcome to this dockerHDDM introduction video. Today, I'll be guiding you through the process of installing and using dockerHDDM on different operating systems. This video is divided into 3 parts: installing Docker, pulling and running dockerHDDM, and an introduction to dockerHDDM's features. In the first part, I'll show you how to install Docker on 3 different systems. For Windows users, first, you need to make sure your system version meets the requirements and has Windows Subsystem for Linux installed. The latest Windows 11 usually comes with WSL, but for other Windows versions, please check the URL provided and configure it in advance. Go ahead and click the download button for the Docker desktop installer. After the download is complete, run the installer. Make sure to select WSL as the backend when prompted during the installation process. Once the installation is successful, you'll need to restart your computer. After the restart, Docker should automatically launch. To verify that WSL and Docker are installed correctly, you can use the following 2 commands. Finally, to ensure Docker is functioning properly, you can run the command. This will confirm that everything is set up correctly. For macOS users, you'll first need to download the appropriate installer package based on your system's chip architecture. Once you've got the installer, proceed with the installation, and feel free to accept or skip any services or settings as they appear. After the installation is complete, you can check the Docker version by running the following command. To wrap up the installation process, make sure to run Hello World to confirm that Docker is functioning as it should. For Linux users, let's take Ubuntu as an example. You can install the Docker packages using the apt command. If you don't require a graphical user interface and plan to run Docker solely from the command line, you can skip the next 2 steps. Simply copy and execute these commands to install the Docker engine. However, if you prefer a graphical interface, you'll need to download the .deb package. Once downloaded, use the following command to install it. After a successful installation, you can launch Docker through the application interface. To check the Docker version, use the following command. And to ensure Docker is working correctly, run the command Hello World as a final step. Moving on to the second part, pulling and running dockerHDDM. Across all 3 systems, you can fetch the latest dockerHDDM image by entering a simple command. This process might take a few minutes, so be patient. Once you see the message indicating that the image has been successfully pulled, you can proceed to launch a container from this image to start using dockerHDDM. One important thing to note is that Docker containers do not have direct access to your local computer's folders. We need to mount a local folder to the dockerHDDM container. We recommend opening a terminal in your working directory and entering the run command there. After dockerHDDM starts, it will provide you with a Jupyter interface URL. You need to make sure that port 8088 is not occupied by another process, then copy the URL and paste it into your web browser to open it. You'll notice that your local files have been mounted to the work directory within the container. Open a notebook and ensure that the code cells are executable. Moving on to the third part of our video, the dockerHDDM feature introduction. Inside the official tutorials folder, you'll find classic tutorials for HDDM that we highly recommend you run and study. They are a great starting point for understanding the basics. We want to highlight the new features of dockerHDDM here. The notebooks in the root directory showcase these enhancements. When loading Python packages, please note that dockerHDDM uses custom-developed versions of HDDM and Kabuki to unlock these new functionalities. Additionally, we'll be using RVZ as our primary tool for Bayesian analysis and visualization. After loading the sample data, dockerHDDM can perform all the original functionalities. But more importantly, we've added some exciting new features. Firstly, you can set the chains parameter to increase the number of MCMC sampling chains and leverage parallel computing, which speeds up the computation. The return inf data flag allows the results to be returned in the inference data format, which is compatible with RVZ for analysis. The inference data object contains priors, posteriors, posterior predictive checks, log likelihoods, and the original data, enabling comprehensive Bayesian analysis. For instance, by using the summary method, you can obtain statistical information about the posterior distributions of parameters such as the mean and highest density intervals, as well as diagnostic information like effective sample size and RAT. Furthermore, with the inference data object, you can perform visual diagnostics on the MCMC sampling results. This allows you to assess the convergence and mixing of the chains, ensuring the reliability of your Bayesian analysis. To consider the impact of experimental conditions on parameters, we can utilize the HDDM regressor to employ a DDM that incorporates mixed effects. Building upon our previous knowledge, we've added a variety of parameters to enhance the functionality of our analysis. The save name parameter allows you to save the model fitting results to a location of your choice. This is convenient for future reference or for sharing your model outputs. With the sample, prior, loglike, and PPC parameters, you can obtain additional insights from the model by accessing the prior sample's log likelihood values and posterior predictive checks, respectively. These provide a more comprehensive understanding of your model's performance. Once saved, the models and data can be reloaded using HDDM load for the models and AZ from netcdf for the inference data objects. This allows you to pick up where you left off without having to rerun the entire analysis. RVZ provides the capability to calculate wake and LUIC for model evaluation. These metrics enable us to select the optimal model through comparison. To use these metrics, it's necessary to have log likelihood values within the inference data. You can ensure these are included by setting loglike true, either during the sampling process or by using the .to inf data method after sampling. Once you have the log likelihood values, you can perform model comparison using the AZ compare function. This function provides a relative measure of model performance, helping you to determine which model better fits your data. While model comparison tells us which model is relatively better, posterior predictive checks assess the absolute performance of a model. You can visualize these checks using plot PPC to see how well the model predicts the data. Ultimately, statistical inference is key to understanding the magnitude of experimental effects. Tools like plot posterior and plot BF allow you to perform inference by presenting the results in terms of highest density interval, region of practical equivalence, and Bayes factors. Just a heads up, if you want to save your work to your local computer, it's important to move any files you wish to keep to the work directory within the dockerHDDM container. If you don't, when you close dockerHDDM, any changes or files outside of the work directory will be reset and you'll lose that data. For a more comprehensive experience, we've included a workflow notebook for you to experiment with. We encourage everyone to give it a try and follow along with the analysis. Please note that when working with real-world data, the process can be quite time-consuming and memory-intensive due to the size of the datasets. It's important to be aware of your hardware limitations and to take appropriate steps to optimize your workflow under these constraints. For more specific guidance on optimization, you can refer to our manuscript, which provides detailed insights into managing these challenges. Finally, we wish you a rewarding and insightful experience on your Bayesian data analysis journey.